My name is Arthur O'Dwyer. This is RPO is harder than it looks. And I've just been informed I have half an hour. So we're going to go fast. Well, in this talk, I'm going to tell you a little bit about return value optimization, and I'm going to tell you also about a special form of it, which I call implicit move, which you get even when you don't get copy elision. We're going to talk about, first of all, what is the return slot and what does it mean to move into the return slot, copy into the return slot, or elide the move entirely. Talk about some rules of thumb, talk about the actual rules, and then look at some test cases and talk about the Clang diagnostic that I wrote as a result of this. What is the return slot? Well, here we have a very simple function, right? Returns the very simplest thing it can. In fact, we have two functions. And let's look at some code gen. Here's what you get when you compile these with Clang. We have apple here, and we have pear here, and they have mangled names. And pear has a call instruction that calls apple, and apple has a move into EAX, and so on. So if you're familiar with x86 assembly, you know the return value usually goes in EAX. Let's walk through this real fast. I'm going to assume mostly that you know how this works. The call instruction does three things. Pushes the return value onto the stack, jumps there, call again, move 42 into EAX, that's our return value, and then return. Return pops an address off the stack and jumps there. We can then add one to that EAX, which is our return value. It's still in the right place to be returned, and we're back where we started, except that the IP is the right value, and EAX is also the right value. And I'm going fast because we have half an hour. If you didn't follow that, don't worry, it's going to get harder. What do we do with big objects? So that example was just an int. It fit in EAX, which is the traditional place we put return values, and that made it really easy. What happens if we have something that's bigger than a register? So here I have a fruit that has 5 ints. It's 20 bytes big, and we can't return it in the EAX register. In that case, we're actually going to add a hidden function parameter. We're going to put that in the first parameter of the function, which traditionally is passed in RDI. And that's going to be a pointer to the return slot, which is an area of the stack allocated by the caller of Apple. They're going to allocate space for the return value, pass you the address. You're going to fill it in. So again, let's walk through that. Right? First, we make some space on the stack. We put the address into RDI. We call Apple. Apple then moves RDI into RIX. That's just a part of the calling convention. I don't fully understand why that's there. And then it just moves everything into the place that we wanted things to go, and we return. Right, and we get the right answer. We, the caller, told Apple where to write its output, and it trusted us. So that was an example of just, they gave us the return slot, we put something in there, we returned. Sometimes it's not that simple. Sometimes I have to create an object and then move it into the return slot. For example, here I have a local variable x and a local variable y, and depending on some condition, I'm going to choose one of them to move into that return slot. So we're going to use simpler schematics from this point on. I have the stack grows down on x86, as we saw in the earlier slides. So I've got the return slot up there. And then below that, I have my return address, where I'm going to jump back to. And then I have the stack frame of the function itself, apples and oranges. So I have 20 bytes for the first fruit, 20 bytes for the second fruit. And I'm going to choose one or the other of them to move from where it is to copy its data up into the return slot when I'm ready to return. I don't know which one I'm going to return until I get there. And so therefore, I can't sort of combine either of them into the return slot. But if it's nothing but apples and I always return x, then I can do something clever, right? I could just do this, where again, it's exactly the same as the last slide, except I got rid of y, and now I always return x, and at the end of the function, I copy x up into the return slot. But the standard actually allows us to combine x into the return slot. So now it doesn't get copied at all, or it doesn't get moved at all. It's just allocated right in there in the return slot, constructed in there, and it doesn't need to be destroyed at the end of the function either, because it is the return slot. All right. So in C++ 03 through 14, this copy elision, where instead of moving the thing, we're just constructing in place, was permitted in many circumstances, but not guaranteed. or it was guaranteed in practice. Every compiler since the mid-90s has done this, but it is permitted but not guaranteed officially. But in C++17, this became mandatory in many circumstances. So now not only can you rely on it in practice, you can also rely on it in theory, which is nice. There are some cases, though, where copy elision is not possible. We saw one of them earlier with apples and oranges, where we didn't know which object we were going to return, and so we didn't know which one needed to be copy elided. There are also some other cases. For example, what if the x that we're returning here is a parameter? In that case, it lives on the stack with the other parameters. Conceptually, I and j really get passed in registers here, but if they were big objects, they would be on the stack too. And so x is allocated by our caller at a particular place, and the caller also allocated the return slot at a different place because it didn't know what we were going to be returning. And so we have no way to elide that copy because we don't control x's physical location. Right? When we're returning a parameter, we don't get copy elision. We cannot get copy elision for technical reasons. The reductio ad absurdum of this, not controlling where x is allocated, is what if we try to return a global variable, right? Static fruit x at global scope, x is somewhere in the data section, and now we're trying to return it. Obviously, we're not going to get copy elision because we don't control where x was allocated in the first place. And then there's one more important case. If this were a smaller room, I would say, who knows what this thing is? I'm going to say it anyway. Who knows what this thing is? It's a durian, yeah, which is a fruit, but it's also something more, right? A durian is a fruit. There's an is a relationship there, but it also has something else inside it, which is the smell. So here I have a function called slapchop, and it takes a fruit, or sorry, it creates a durian, x, and then it returns it, but it returns the fruit. It slices it. And when you slice it, you release the smell. The smell is now not part of the thing we're going to be returning. We're only going to return the fruit part. And this is a problem. We can't elide this copy. We can't allocate x into the return slot to begin with because x is bigger than the return slot. The return slot's only 20 bytes. The durian itself is a very large fruit. It's 32 bytes because of that smell. And so here, x is of the wrong type for constructing into the return slot. We're going to have to allocate it down here and then move it up. So here are the rules of thumb for RPO. This is what I used to tell people before I started, reading about this. That there were basically very simple rules in C++. Number one, there are two kinds of RPO. There's unnamed RPO, returning a PR value, such as these examples. That's going to trigger copy elision. It's just always going to get allocated right into the return slot. You're golden. Named RPO is this special case in the standard where if we have a named variable x and we return x by name with no, you can have parentheses, but you can't have any other functions surrounding it. But as long as you return it by name like this, it'll trigger copy elision, except in those few corner cases we just covered, which for physical reasons cannot be copy elided. And the consolation prize is that even if copy elision doesn't happen, in this case where we return by name, you'll still get something called implicit move. And I say called because I call it that. Implicit move is when you return a local variable by name, it will try to do copy elision, but if it can't for technical reasons, such as being a parameter, a global variable, whatever, the compiler's overload resolution will treat that name x as an R value, and you will get a move, not a copy. So for example, here I have std string identity. It has x is a parameter, so I cannot do copy elision. But what I can do is when I say return x, the compiler is actually going to treat x as an R value. And it's going to use std string's move constructor, not its copy constructor, to move out of that parameter. So I'm still going to get very efficient code. And this has been true since C++11. And it works great. And return std move x, probably don't even need to write that. Right? If you do write that, that might actually inhibit copy elision, inhibit named return value optimization, because now you're calling a function on x. It's no longer returned by name. And it's not necessary, because anytime you say return x, it's going to return by move anyway. All right, so that was not actually the truth. You want the truth. For that, we're going to digress into an example. Little war story here. This is some slightly anonymized code from a real code base. Here we have a C API. This is an API from way back, legacy API. It's all written in C. It's all pointers and whatnot. And we have this sort of expression node thing called a Cexpr. And we have a bunch of functions that manipulate it. And then someone gets the nice idea to take the, and you all have seen code like this, right? It's all pointers and you malloc things under the hood. We're going to wrap this up in a nice little C++ API so that we can use value semantics with this and we don't have to worry about mallocing and freeing and newing and so on. So we wrap it all up and we say a capital Cexpr is going to be a very thin wrapper around the pointer, and it's going to have a copy constructor that calls expr clone, and it's going to have a move constructor that just copies the pointer and nulls out the original, and it's going to have a destructor. It's a RAI type. And then we can make subclasses that also wrap a pointer and just a pointer, but they add behaviors. They don't add any data, but they add behaviors. So here we have a sexpr int. You can get the value out of that. Sexpr list has a length and an append. And has some details there, which I'll skip over. And we have some C++ functions that return Cexprs by value, because now it's an RAI type. It has value semantics. So I can have this config manager type thing that builds up a representation of an expression. In this case, it's a list containing 1742 hike. And it's going to return that. Now, it builds it as a list, because that's the thing that has the append method on it. But it's going to return it as a regular old sexpr because the caller doesn't necessarily know. This is obviously a virtual function, and in our particular case, we're returning something that represents a list, but someone else might return something that represents a dictionary or something like that. So we do this and we ship it, and QA says, you're spending an awful lot of cycles copying strings and copying lists. Why is this happening? Well, that is very strange, right? You told me that when I say, return CFG, and I'm returning it by name, it should treat CFG as an R value, and therefore it should move, and I should get the move constructor that just copies the pointer. Why is it copying? All right, let me tell you the real deal. Here's how it really works. The actual rules of implicit move. So the rules were slightly different 5 years ago, but the rules were posthumously amended by a defect report, and they were amended to say something like this. If the expression in the return statement is a possibly parenthesized ID expression that names an object, blah, 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 overload resolution to select the constructor for the copy is first performed as if the object were designated by an R value, right? This is what we expected to happen. If the first overload resolution fails or was not performed, or if the type of the first parameter of the selected constructor is not an R value reference to the object's type, possibly CV qualified, overload resolution is performed again, considering the object as an L value. So if the first overload resolution failed, obviously we fall back on copying, if it's something that cannot be moved for some reason, or if there's no move constructor. But also, all of these other constraints, and every bolded word causes a new failure mode. So what went wrong here was slicing. Right? We have the sexpr list, and the constructor that we want to call here is the move constructor of Cexpr. But CFG's type is Cexpr list, and so the constructor that we find with overload resolution when we try to move out of CFG is not, it is Cexpr of Cexpr ref, and that type is not Cexpr list ref, it's Cexpr ref. It's a base class. And so it is not exactly the object's type, and so the compiler does not do the optimization. Here's another example that came up in the past year. We have this thing over at SG14 called in-place function. It's just like std function, but it holds the object within itself. And there are two ways of sort of writing conversions between these functions. If I have a function of one size and a function of another size, and if the destination size is at least as big as the source size, then I should be able to construct from one to the other. Here I have a converting constructor that says, I know how to construct myself from the object that you gave me, which was smaller. I will steal all his guts and put them inside myself. This is the traditional C++ way of doing it. Someone active on the project suggested, oh, it would be more philosophically correct to go the other way and to say, when I am being converted to a function which is bigger, then I will lend him my guts if I can. Right? And this matches our mental model a little bit better. It's self-disemboweling instead of someone else disemboweling, which is a little bit rude. And unfortunately, when we looked at the unit tests for this, suddenly in this example we're spending a lot of time in std strings copy constructor. That's the std string as the capture of that lambda there, the MSG. We're copying the lambda, therefore we're copying all of its captures, therefore we're copying the std string, which is expensive. And we're copying the lambda because we're calling the copy constructor rather than the R-value conversion operator that we thought we were going to get called. And the reason for that is that after the patch, it finds this conversion operator. We do the overload resolution as an R value. It finds the conversion operator. If the first overload resolution fails or was not performed, or the selected constructor is not an R value reference, and this is not a constructor, it's a conversion operator. So compilers will not find it, and they will fall back to doing the copy. Except, of course, for GCC and ICC, which do the move and not the copy. So why converting constructors? Why did we put this thing in C++ where there's a rule for constructors that doesn't also apply to conversion operators? Do we just hate things that are more philosophically correct? No, there's actually an important reason that this got retroactively inserted into C++ 11, and that is unique putter. Without this rule that return P would do a move when it could, this would, if return P there did a copy, it would be trying to copy a unique putter, and that would not work. That would just not compile at all. So it was very important that if you want this code to work, you've got to make sure that it moves when it can in such a way that I can take a unique putter of config manager impl and get a unique putter of config manager out the other side. And the way I make that work is I call the constructor that takes an R value. There's no need here to call a conversion operator, and so they just conservatively didn't put in a rule that said you could call conversion operators, but you can call converting constructors that take R values. And the standard library loves move-enabled converting constructors. They have them for unique putter, shared putter, std function, std optional, expected will have one, variant. All of these examples use converting constructors. None of them use conversion operators. So can we get the compiler to warn us when we write return x and returning by name, and that would make a copy, and it would actually be more efficient to say return std move of x? We can definitely do the opposite. The opposite has been there forever. But as of the beginning of the year, the reverse was not correct, or was not there. This is a puzzle. Right, so I went and added one. Unfortunately, we have like 5 minutes left, but I gotta skip all of this. Oh, this is so good. But the punchline is, ship it. As of May 2018, Clang does have a warning called return std move, and it is enabled by wmove and by wmost and by wall. So if you use any of those, particularly wall, which you should be using, you will get this warning if you use Clang trunk, and that is awesome. There are also 2 papers coming before EWG in San Diego. One of them by me, one of them by David Stone, which has already been seen by EWG, and right. We'll do some examples. What do we think happens in some of these cases? These are the examples that will eventually get fixed by the paper. This is too large, and I have too little time to shout out the answers. So here are the answers. When I throw W, it will do an implicit move. Copulation is technically permitted, but nobody does it for technical reasons. When I return out of a parameter, we saw that does an implicit move. And when I throw out of a parameter, technically that needs to be a copy according to the paper standard, but everybody except GCC does the right thing. But there's a proposal that I wrote to make it do the right thing on paper too. Here we have another example. This is the in-place function example. We have one thing with converting constructors, one thing with conversion operators, and converting from widget to from, that works great. Converting from to widget, that does a copy. We propose to fix this. Example number 3, this one I wasn't even aware of until after I wrote the paper. This is something called a by-value sync. Thanks to Barry Rebson for bringing this one to my attention. This common trick to avoid writing multiple overloads and just put the burden on the compiler to figure out how do I get that widget in the first place? Well, it turns out that disables implicit move, unless you're on GCC. We're going to fix that. This is the slicing example. If I have unique putters to derived and base, I can move from a unique putter of derived to a unique putter of base. But if I have a regular old derived and I try returning it by value, and I slice it to a base, that will do a plain old copy everywhere except GCC and Intel. You can see that the compiler writers do not really agree on what should happen here, and I think that is not necessarily intentional. I think the rules are just so convoluted at this point because of all that stuff that was bolded earlier that compiler writers may not necessarily know what goal they're trying to accomplish at this point. But we're going to remove all those bolded words, and then it will get easier. Moving out of an R-value reference, if I take an R-value reference as a parameter, or I have a local variable of R-value reference type, it should be relatively unsurprising that I don't know what this reference refers to, and therefore I need to do a copy. The other paper, on which I am not a co-author, does propose to make both of these work and do implicit moves. I find that a little bit scary, but probably a good idea overall. We have found in practice there are a lot of programmers out there writing code where they expect this to move, and it doesn't. So having it match expectations might be a good thing. And then another example, I was just in Dan Sachs' talk on making new friends, and he had a couple of these overloaded operators, implementing plus in terms of plus, or plus in terms of plus equals and things like that. And I thought, hey, that would make a good last slide. I should put that up here, because it's quite often that you see something like number 17 there, where I'm trying to implement operator plus in terms of plus equals, and I just say, oh, I can just combine all that. But of course, if operator plus equals returns an L value reference to this, well, you're going to get a copy. There is no proposal, as far as I know, related to assignment operators or to assuming that an assignment operator always returns this. If you want to write one for San Diego, come talk to me. And we have 3 minutes left, so I could maybe take some questions.
Hi. The conditional return, which was at the beginning.
Yes.
What would happen in that case?
The conditional return at the beginning, what happens in that case? Well, that entire conditional expression with the question mark, well, A, there's a std move wrapped around it, but that entire thing would then be an R value at that point because of the std move wrapped around it.
Okay. Without the move? Without the std move, that would just be an expression of L value type, and so it would make a copy, as far as I know. Even after all the papers?
Even after all the papers. This arbitrarily complicated expression is very hard to mess with.
So I guess it seems like it would have been a lot simpler just to change the wording to treat this expression as an R value instead of all the constraints. So I'm just curious, did anyone ever come up with an example where if the constraints weren't there, then sort of a flip side to all of your examples where, oh, look, if we loosen the constraints, then you get this insane behavior, which also sucks? Is there an example like that?
No.
Okay. That's good.
In the sense that, because the warning has been in Clang now for, I don't know, going on 6 months, I think, there have been a lot of open source projects that have run it on their code base, and there have been several bugs fixed as a result, and one bug report in the sense that they said, well, our type is cheap enough that we don't actually care that it makes a copy. So this warning is kind of noisy. But it was still correct that it was making a copy instead of a move. And a move would be slightly faster. They just didn't want to type the extra 10 characters to put the std move around it.
Thanks.
In your CXper override example.
Let's see, that would be, yeah.
Is the guidance not better set as like just return CXper list from that override, and then it'll just slice on assignment as opposed to...
could we just return CXper list from this override because we can do covariant?
An overridden method.
Because we can do a covariant return here?
Yes.
Possibly yes. It would still be nice if we wrote this not to have it secretly do a copy.
True.
Yes. I imagine it might be hard to teach about the covariant returns, especially if you have to teach about all of this RVO stuff at the same time. You can have 2 complicated features or 0 complicated features. And with that, we're done.